Hi students, welcome to Inside Physics. Today we are going to discuss about the quantum free electron theory. So this was proposed by Sommerfeld in 1928 by considering some of the classical principles and also including Pauli exclusion principle and Fermi-Dirac statistics. By considering these two principles, he postulated the quantum free electron theory features like, see, the first one regarding the eigenvalues. So eigenvalues give the quantized energy levels and also represents the set of energy levels. So the eigenvalues are nothing but the represents the quantization of energy levels. And the second one, see, all the electrons revolving in the orbits are arranged in the orbits according to Pauli's exclusion principle. So second one, according to Pauli's exclusion principle, the free electrons are arranged in the material in their revolving orbits according to this principle. And the third one, see, all the electrons revolve in the orbits and they are bounded to certain boundaries, that is the potential barriers. Inside the material, the electron is in a potential barrier. That means the potential is constant across the material and it has a definite boundaries through which it cannot overcome and pass through that boundaries. That is why it is called a finite potential well. So that is the third one. It is moving across a constant potential across the material or across the lattice space. So the fourth one. See, there are some attractions between the electrons and lattice ions, obviously, and there are also some repulsion between the electrons and the neighbor electrons. So, there is some repulsion between the negative charged electrons, and there is an attraction between the lattice ions, that means positive ions, and the electrons, and the same way between nucleus and electrons. So, these attractions or repulsions are, here we ignore the attractions and repulsions. So, based on these principles, the quantum free electron theory was proposed by the Sommerfeld. So, now, according to this theory, the electrons were considered as a Fermi gas. What is a Fermi gas? So, the electrons which obey the Pauli exclusion principle to occupy the energy levels and the continuous nature of electrons moving across all directions in the material is like a gas, moving like a gas. So, there may be millions and trillions of electrons. So, all together they move like a cloud or gas. So, they cannot be called as an electron cloud, or because they are obeying the Pauli exclusion principle, they are also called Fermi gas inside the material. So now our aim is to calculate the density of energy levels. So density of energy levels gives what? So if you calculate the density of energy states, we are able to identify the material is a very good conductor. How much is the energy levels? It has a number of energy levels. Number of energy levels per unit volume is nothing but density. So energy states. So energy states are nothing but the orbits in which the revolving electrons are moving. So now we consider a procedure to identify the density of energy states. So here we consider a material and we imagine the shape, that means the minimum structure, a lattice or a unit in the form of a cube. If you imagine a cube and with some crystallographic axis, okay, so this is a sample you are given, and this sample is imagined in the form of a cube of side L. These are the crystallographic axes, okay, X, Y, Z. This is the origin. So now we have a cube structure and with the side L. So here the energy of an electron, of a free electron moving inside a material, when we apply the Schrodinger wave equation to an electron, the quantized energy levels are given by E is equal to h cut square by 8m capital L square n x square n y square plus n z square. So this is the energy of an electron, and this is a quantized energy level. When we apply the Schrodinger wave equation to an electron, why we apply Schrodinger wave equation means the electron is associated with a matter wave. So if because of that wave characteristics, the electron can have only finite values when it is moving inside a potential barrier, inside a potential well with definite potential boundaries. So the wave nature provides the electron to have only some finite values of energy levels, not all the energy levels. So here the origin, see this xyz coordinates, xyz coordinates gives us the directions inside the crystal, and these are called crystallographic axes. So what is n, x, n, y, n, z? These are the points, we call them as quantum point or quantum state. So inside the quantum space, we represent a quantum state of an electron by a point by considering nx, ny, nz as the three coordinates of that particular point. If you consider a point n here inside the quantum space, inside this cube which is considered as a quantum space, the quantum state of an electron is considered by this quantum point, and this nx, ny, nz are the coordinates of this particular point. So the energy of the particular electron is represented by nx square plus ny square plus nz square as per this equation. As per this equation, we can take it as this as an energy term, and n square is equal to nx square plus ny square plus nz square. So here if this is a point and we draw a radius from origin to this point where the radius is equal to n, then if you imagine a sphere of radius n around this inside this cube, so then all the electrons on the surface of the sphere of radius n will be having the same energy levels, same energy. So this quantum space, inside this quantum space we have drawn a radius n, and we have imagined a sphere of radius n, and the surface of the sphere is having the same energy on the each and every point of that particular sphere. So the energy levels inside the sphere on the surface of the sphere is given by, so what is the what are the all energy levels that can be had in the throughout the volume of the sphere, means we can have that in the equation like n of E, the number of energy levels in the volume of a sphere is nothing but 4/3 pi n cube. So n is the radius we know that the radius, because of the volume of the sphere, is as per this formula r cube 4/3 pi r cube, where r is the radius. Now we have the n values like c nx, ny, nz, where we will get same energy levels even for different values of nx, ny, nz. So the energy level, the energy value of a particular set of energy levels is same, even the values of nx, ny, nz is changing. So here the values of n can be only positive. The values of n can be only positive values, because the principal quantum number cannot have the negative value. Okay, so the energy levels of an electron can be understood because of four numbers. Those are nx, ny, nz, and spin quantum number, where ms is equal to plus or minus half. So these are the four quantum numbers that we can have, and we can understand with these four quantum numbers the state of a free electron is determined by these four quantum numbers. So where nx, ny, nz are the principal quantum numbers in the direction of x, y, z direction, and ms is the spin quantum number, where spin of electron is either plus half or minus half according to its direction, either clockwise or anti-clockwise. Now, if the n is having only positive values, the space we are considering must be in the positive direction of crystallographic axis. So in this way, we will having an octant. An octant means if the sphere is cut into 8 equal parts, one of the part is called an octant. So the space we are considering across the crystallographic axis is having one of the octant in the positive side of crystallographic axis, that we can represent an octant like this. So this is the positive side. You need to imagine. So whatever I am telling, you need to follow me and understand what I am exactly try to explain. Here there is a space around this crystallographic axis, but this is only an octant. I can draw it in a better way. So if you consider a point n here inside the space, and this is having a radius n. So here we draw some lines here. So this is n z, n y, is n x. So this point is having three coordinates nx, ny, nz. This is an octant. Okay, the one of the 8 parts of a sphere is called an octant, and in that octant we are imagining a sphere of radius n. Okay, now the volume of an octant is 1/8 of the actual volume of the sphere. So the number of energy levels in one octant is 1/8 4/3 pi n cube. Okay, so if we consider a sphere of radius n plus dn, so the energy levels which are having in this spherical shape can be understood with the representation E plus dE. So the extra the extra distance dn gives an extra energy of dE. So if we consider a sphere of radius n plus dn, we will be having an energy levels of E plus dE. Now how we can write this means n of E dE. See here, in place of this n we can put as 1 by 8 4 by 3 pi n plus dn whole cube 4 third pi n plus n plus dn whole cube. So here n of E dE means this is the minimum energy that we are having in an octant at the with the sphere of radius n plus dn. So now this is can be represented as E plus dE. Okay, and now we need to get the value of number of energy levels in that particular distance of dn. So how to get that one? The number of energy levels in a particular energy band, that's radius dn means n of E dE. How to get this one? This is E plus dE and this is energy for an octant. So now we subtract this from this. How we write? 1 by 8 4 third pi n plus dn whole cube minus 1 by 8 4 by 3 pi n cube. Okay, see, this is a cubical expansion and we ignore the higher terms of dn because the value of dn is very small. So if you simplify this one, if you are going to simplify the relation, it will be taking much more time and it will be a lengthy relation. So we will simplify and I will make it as a direct relation pi by 2 n square dn. You can do it on your own. Try to simplify the terms. It is very easy. Neglect the higher terms of dn. That means dn square, dn cube. You neglect and only you consider dn. And finally, the value comes to be pi by 2 n square dn. Okay. So here this is the value. Now from this we can understand what is n. See here, if you put E is equal to h cut square by 8 ml square and n square, where nx, ny, nz is equal to n square. So now if you take n square is equal to E 8 ml square by h cut square. Okay. If you consider n, that means squaring, taking square root on both sides, this will be coming as 8 ml square by h cut square e to the power of 1 by 2. Okay, 8 ml square by h cut square whole to the power of into e whole to the power of 1 by 2. So if you differentiate this one, if you differentiate this equation, this can be termed as dn is equal to, so this term is having a square root. Okay, so now we will take it as 1 by 2 into 8ml square by h cut square into dE. Okay, so this is a small m, mass of electron, and half 8 ml square by h cut square into e power 1 by 2. Okay, so if you differentiate, this will be coming as 4 ml square by h cut square dE. So 2 is going 4 times in 8. Okay, so now after differentiation, this has come to be n dn is equal to 4 ml square by h cut square dE. Now what we know here, n of e dE, right? N of e dE is equal to, we can write this as pi by 2 n into n of dn. Okay, so this is what we want, the energy states, number of energy states in a particular energy level with in a space of radius dE. So here what is n? We already know n is nothing but, here see, 8 ml square, 8 ml square by h cut square E power 1 by 2 n. What is n dn here? Into 4 ml square by h cut square dE. Okay, so 4 ml square by h cut square dE. n and n dn terms are written here as per this. N is equal to this one, n dn is equal to this one. So now we simplify this one. Okay, now see here, the number of states, energy states available for an electron occupancy is double this number. How we can say this as double? That means, see, if you rewrite this one, you can simply exchange the terms. I will write in the above. See, so here some term is missing. I think pi by 2 into n into dn. So here if you multiply this numerator and denominator with 2, what we will get? Pi by 4 into 8 ml square by h cut square E whole power 1 by 2 into 8 ml square by h cut square dE. So from this step what I did is I multiplied numerator and denominator with 2. So this is n of E dE. Okay. So now we simplify these two and make a final equation. Pi by 4, so 8 whole power 1 by 2 here, and 8 power 1. So what we can write here? Here pi by 4 into, if this term is having an energy level and the number of energy states available for electron is double this, so we have to make this double. Before that we need to simplify it. So pi by 4, 8 ml square by h cut square whole power 3 by 2 into e power 1 by 2 dE. So these two terms are added because power 1 by 2 plus 1 becomes 8 ml square by h cut square 3 by 2 into e power to 1 by 2 has been put aside. Now if you observe this, this is an energy level for an electron in a particular space of radius dn. But the electron has two spins. So for each electron there are two energy levels available. That means we have to multiply this with 2. So the actual number of energy levels for an electron is n of E dE is equal to, when we multiply it with 2, it becomes pi by 2. Okay, and when we multiply with 2, and we can write it as 4 pi by h cut cube. This I am rearranging the terms. This is, see, pi by 2, when I multiply this with 2, this becomes pi by 2, and I have put the value of 4 outside. So then what happens? This becomes 2m. See, the values we are exchanging here, 2m power 3 by 2 into L cube into e power 1 by 2 dE. So this has become pi by 2, and I have brought this 4 outside, and this h square to the power of 3 by 2 will become h cut cube. Okay, now I can write this as 2 to the power of 2 exchange with 2 times pi by 2. Okay, when, see, this 8 to the power of half means 8 cube, 2 into 3, and this 3 by 2 has become 2m to the power of 3 by 2. Okay, so 2 cube is nothing but 16, and this pi by 2 value 4h by h cut cube gives the energy levels. Now what is the density? Now we are actually try to find the density of energy levels. How we get the density? Now with this formula, 4 pi by h cut cube 2m to the power of 3 by 2 into L cube into e to the power of 1 by 2 dE is nothing but the energy levels, number of energy states. So number of energy states by volume, number of energy states by volume gives the density of energy states. So density is nothing but value per unit volume. Now we are considering the density of energy states. So number of energy states per unit volume. That means if we divide this with L cube, volume of a cube is nothing but the volume of a cube with side L is nothing but L cube. So if we divide this with L cube, this will become okay. So Z of E, Z is nothing but the density of energy states. So this represents the density of energy states in a particular space which is having a radius of dn. So this is how we find the energy of the levels, density of energy levels. So, so we move to the next topic in quantum mechanics with another useful derivation in the next video. Thank you.